but I see on my other screen, because I've got a second screen, of course, set up so I can see what you're seeing. But it's kind of lagging, so hopefully that clears up. But all right. So, oh shoot, where are my notes for today? Here. Okay. So, yeah, it's really lagging. Is it lagging for you guys too, or are you seeing my there?
Yeah, your voice is also kind of lacking.
Oh, really? Oh, shoot. That is not good, is it?
And I think okay, it's okay.
It's okay. I don't know. Let me know if it becomes a problem. My husband is promising he's not online, so he can't be blamed, I guess. So hopefully it'll get kind of sorted out. I didn't have any complaints in the earlier session, but maybe they just weren't paying attention. That's always an option. All right, so today we're just going to keep going through chapter 8. Chapter 8, remember, is just like a compilation of all these different methods that we could use, different techniques to kind of keep in mind if you're doing Anova, right? Kind of alternatives. But one thing, I finally marked your test 2, so you should have gotten an email from Gradescope to see your test 2. In general, I was very pleased with how you guys did on test 2. I know I sprung it on you guys, but I was very happy with what I saw. So nice work. I know that's tough, but hopefully we're on to easy street now. So, well, hopefully, I guess I'm in charge. We're on easy street now. So you should have gotten an email from Gradescope to see your test 2. If you're having trouble setting your password, and this was in the email that went out too, and I kind of added a second blurb myself. There's a default email, of course. So if you have troubles setting your password, email at gradescope.com. But also let me know. But also let me know, and I will send you your test. Send you your test and feedback. So just let me know, but also send an email to help@gradescope.com because they seem to be having troubles. Some people, but not everyone. Some people are getting on there just fine, so we should let them know. But since I'm just using it for test 2, it's not that big of a deal. I can just email it to you. All right, I'll post the solutions. I have them. I just have to just scan them quickly and post them. So I will post the solutions as well. Okay. Any questions? You guys just unmute yourselves if you do.
Yeah, you were talking about the final exam in the last class. So can you enlighten us? What's the situation?
Oh, So the final exam, what I've decided to do, I thought who got the highest? I'm pretty sure it was Sai. I'm pretty sure. Okay, so, but there were some good scores on this one, so I'm happy. Oh yeah, so the final exam, yeah, what did I say last day? Was I kind of just vague? Oh, we just started. Just went into it. Okay, can't remember what I said. So the final exam is not really going to be a final exam. See, it's lagging again here. Oops, gives me time to clean up my writing a little bit. The final exam, it'll just be like a wrap-up test on things covered after test 2. Okay. And most likely it'll just be a Moodle quiz. A Moodle quiz worth 10%. So I'll try my best to make it kind of nicer than test 1, but nicer looking at least, but it'll just be kind of a Moodle quiz, just touching on you know, the big ideas. So nothing really deep that I would say is going to be on this thing. It's just a wrap-up test. So really quick, kind of, and because it's worth 10%, we can talk about if you want to have it in oh, so yeah, so is it compulsory to give the final? No, it's only 10%. So or do you mean for me? Do I have to give a final? So the question was from Sahil. Say that again.
Is it compulsory final or we can skip it? Like,
you can skip it if you want, but it is 10% of your grade.
okay, so for the grades, okay, thank you.
Yeah, so if you don't want to write it, that's fine. But it will just be online, right? So it will just be a Moodle test. And so we'll just set a time. And like I was saying, so because it's just a Moodle quiz and it's only worth 10%, we're allowed to have it in the last week of classes. So if you guys prefer, we've got 2 options. Our first option is to write at the regular exam time, right? But on Moodle, so it's just, you know, from home, which was April 21st at 9, I think. I think it was 9. Or the second option is to write it during class time. Write it during class time on April 8th. April 8th, I think, is the Wednesday. I hope. So we've got 2 options. So we can write it during the regular exam time, or you can write it during class. We will have to decide together which one you want to do, right? Which one you prefer to do. Kind of get it over with on April 8th, because it satisfies the less than 15% of your grade criteria. Or if you want to put it off until April 21st, either way, it's just going to be on Moodle, right? So the quiz will be on Moodle, taken from home, wherever you are. All right. Okay. So I'm seeing here, so Hill votes for option number 2. Oh yeah, so are we all here? 1, 2, 3, 4, 5, 6, 7. We're mostly here. Okay, so if you vote for, let's see here. Everyone knows how to raise their hand. If we vote for option number, well, it looks like option number 2. So if you vote for option number 2, raise your hand now. 2. So it looks like I'm getting, oh. So I've got
Ellie,
4
can
hands.
you raise your hand for any option?
Say that again?
Can you raise your hand for any option that suits you?
Yeah, so for option number 2 is the one we're raising our hands for now. I can't actually see, can't see who is, oh, here we go. 1, 2, 3, 4, 5. Okay. So that's still only 5 out of 10. Oh. Okay. Looks like we've got 7 for option number 2. Okay, thanks guys. Very democratic way here. So what I'll do is, this one got 7 votes. And if I misunderstood that, then just let me know. But this is the one that we'll do. Okay. Might be nice to just get it over with. It's such a small portion of your grade. Another thing that I wanted your feedback on was, do you want to do more labs, or the one that you handed in, do you want that one to be your last one? So do you want to do more labs? We'll do the same thing. How about if you vote yes for more labs, raise your hand. Oh, now I can't tell if, besides labs, do we have any assignments? So the assignments are only the ones that I've posted on Moodle. So it's just those Moodle quizzes. They're usually, 5 questions or so long. So the assignments, oops. Okay, cool. Assignments are the Moodle quizzes posted for each section. Oops, for each chapter, I guess. All right, so if you, so is lab 5 the last one? That's what we're trying to decide. Do you guys want to have more labs or no? I'm seeing some hands up here. So you guys want to have more labs? Okay. I'm seeing 3 votes. And again, I don't know, it's hard to tell. I'm seeing 3 votes for more labs. What we can do Eugene says, I mean, if our course, yeah. Well, I mean, I can always make up more labs. Is it possible to have labs just for fun? Of course it is. How about we'll do one more lab then. So here, because this feels kind of undecided still, so we will do one more lab. Sandeep says, no more labs, please. But how about this? So there's going to be a total of 6 labs. Oops. Because you just handed in lab 5. Oh, okay. Sandeep says no more labs. For fun labs, a big yes. Logistic regression. Yeah, so we are supposed to be covering logistic regression, and that is the one that I'm thinking that we I'll do a 6th lab on, but you'll have more time to do it. So we'll do one more lab for a total of 6 labs. But how about this? I will use your best 5 labs out of 6. So if you don't want to do lab 6 can be by the 21st. Yeah, that works for me. How about that? So we'll do one more lab. And then I'll use your best 5 labs out of 6. So if you don't want to do lab 6, then that's fine by me. I don't really care. It's just if you want the opportunity to boost your grade or whatever. So I'll do lab 6 will be on logistic regression, which is chapter 9, which we haven't gotten there yet. So so you'll have to wait a little bit for lab 6. But how about we just set the due date just as Nitin suggested, due April 21st. Awesome. Okay. So looks like everyone's okay with that. All right. So wheeling and dealing here at midnight. So we will have a lab 6. It's going to be on logistic regression, but like I said, I'll just take your best 5 labs out of 6 for your lab mark, and that should secure a pretty high grade for everyone. So hopefully that's good, and even if you don't want to or don't have time to do the last lab, then that's fine. Okay, it's kind of in your hands. All right. Looks like I'm making a quiz for next week. Yikes. Put that on my list of things to do. Better do that. Quiz for Stat 240. Okay. All right. So any questions, comments, concerns before we start here? A lot going on here. Annabelle says no. Thanks, Annabelle. Awesome, good. Okay, let's get started. Okay, so we're gonna keep going through chapter 8, like I said, which is just a collection of things that we can do besides Anova or kind of in addition to Anova. Let me see here. Lab 5. Okay, so I know you guys really doubt yourselves. How about this? So I'm gonna mark lab 5 and then I'll post solutions to lab 5 and you can have a look. I can't even remember what I made you guys analyze for lab 5, but I guess I'll see when I've marked it. So yes, I will post kind of an example solution to lab 5, but if it's anything like the other labs, right, there's lots of different options. And so as long as you used kind of the methods, size not sold, he says sure. All right.
Yes.
Then I'm happy.
But when you're using the power rule,
yeah,
if the value is between 1.6 to 1.7, so what transformation are you going to use?
So is the slope 1.6?
No, after the calculation and the power.
Oh, so the power is roughly 1.6.
Yes.
Yeah. Okay, so then I could leave it as is, or I could punch it up to a square, right? So leave at 1 or square it. You could do, I would always just probably try to leave it as it is. Or you could do both calculations, right? You could leave it at 1 or you could square it, right? And so you could do side-by-side comparisons. So compare the results. It would be very confusing if you got different results, but usually you don't, right? And so then you would argue, okay, I'm gonna just leave it at 1 instead of complicating it with a square.
Yes, thank you.
No worries. And that was for lab 5, right?
Yes.
Thank you. Cool. Nice. Do that. Okay. So let's see here. So we've got topic 8.3. So these are just little topics, little bite-sized topics. We can do comparisons, and we can also talk about contrasts. So comparisons and contrasts. Okay, I'm just thinking about how we should proceed for the rest of the sections, but we'll see how far we get to today, and then I'll make a decision. Because what we might do is we might just go into logistic regression and leave the rest of the topics just for optional reading. But we'll see, like I said, we'll see how far we get this week, and then, yeah. So comparisons and contrasts. So we've done comparisons. Comparisons are things like a 2-sample t-test. And so in a 2-sample t-test, t-test, we do a comparison. So that would be a comparison, and we test something like mu1 minus mu2, is it equal to 0, for example. Right? And so we're comparing mu1 and mu2. And so what we have in an Anova setting, we do comparisons using the t is the y1 bar minus y2 bar over the square root of the mean squared error times 1 over n1 plus 1 over n2. We've seen that before when we were doing our comparisons. And so here we use the mean squared error in lieu of our standard error, or our standard deviation, just because we're in the Anova setting, right? And so we assume that they all have the same standard deviation, and so we can use this mean squared error instead of the standard deviations. So those would be considered comparisons, right? If we want to do contrasts, what we're saying is that we want to look at more than 2 groups. So if our question, right, our research question, so if our question involves more than 2 groups, we need to do, a contrast. Or actually, I jumped the gun. Guys. Not a contrast quite yet. A contrast is a specific linear combination. We need to, we need to use, use a linear combination. Of means, which is going to look something like C1 mu1 plus C2 mu2 plus all the way up to however many groups we have, Ci mu I. Okay. Notice that if we're looking back at mu1 minus mu2, right? If we want to test mu1 minus mu2, well, we would just replace this here, right? To test mu1 minus mu2, use C1 equals 1 and C2 equals -1, and all other Ci equal to 0, right? That would bring you back to just comparing 2 different means. And so here we've got a combination of means with all these different coefficients. With this, a linear combination of the means, because we've got all the means, all the possible means, all the different groups, and each of them get a coefficient, and those coefficients can definitely be 0, right, if you don't want to consider those groups. And so we use C1 Y1 bar, right, plus C2 Y2 bar plus Ci Yi bar as our estimate. Just like we used Y1 bar, Y2 bar for our estimate here, right, if we wanted to compare mu1 and mu2. So nothing is really different, right? But now if we're doing these linear combinations of the means, right? So essentially we're going to lead up to contrasts. then this would be our estimate. Right? Our estimate has standard error, as the standard error of the root of the mean squared error times sum from I equals 1 to I, right, for each of the groups of Ci squared over Ni. And so each of the coefficients squared over Ni, right? If we go back to here, mu1 minus mu2, if that's what we're testing, our estimate is y1 bar minus y2 bar. C1 is 1, C2 is negative 1, right? So the sum of from I equals 1 to 2 in this case, right, would be 1 squared over n1 plus negative 1 squared over n2, right? And so this isn't that different. Right. For two groups, right, y1 bar minus y2 bar, the estimate, the standard error would be the square root of the mean squared error times the sum of C1 squared over N1 plus C2 squared over N2, but C1 is 1 and C2 is negative 1. So this would be the square root of the mean squared error of 1 squared 1 over N1 plus negative 1 squared, which is also just 1 over N2, right? And so we, therefore, they are the same, right? It's just an extension of, now we're allowing for multiple groups, right? Multiple means here instead of just two means that we want to compare. So here's where I jumped to earlier. So these linear combinations, right? Oops, not in my pointer mode. So these linear combinations can take on any sort of linear combination. But the most interesting ones are if we have contrasts. So linear combinations of means can take many forms. But usually, the most interesting linear combinations, linear combinations are contrasts. And so a contrasts are when the coefficients add to zero, right? Which we had here, we were just talking about just two groups, right? Oops. Just two groups, C1 is 1, C2 is negative 1, right? This adds to 0. 1 plus negative 1 adds to 0. And so, and all the other ones are 0. So this is a contrast, right? And so, oh, it's not showing my pointer. There, weird. It must be really laggy on your end. Sorry, guys. I'm not sure what to do about that. So, so the contrast is when the coefficients add to 0. Okay, it's with me now? Not quite. Okay. anyways, that must be annoying, but like I said, I don't really know what to do about it. So the coefficient add to 0, right? And so what we have is if we have a contrast, then C1 plus C2 plus all the way up to Ci must be 0. Right? And some Ci, C subscript I, might be 0, right? And often, you know, if you're not concerned with a group, you can just let the coefficient be 0. Yeah. There. Okay. So, in the textbook, it goes through, and you can have a read through. There's a couple of different examples, but if you have a read through example 8.8, example 8.8, for a full example using contrasts. I do want to look to it is that the original F test, the first F test that they ran, is actually not significant in example 8.8. And so notice that the overall F test, is not significant. But we can do if they were already planned. So if they were already planned before collecting the data. Okay. So that's important, right? So the difference here is that, okay, well, we should always do our F test. So if we're handed data and we're saying, is there anything going on in here? You should always do the F test to see what's going on. And then if there's nothing going on, then you wouldn't keep going, right? Whereas if you've gotten funding and you've decided, you know, you've sold some people on collecting this data and doing this analysis, even if you found that your F test was not significant, you had and do the comparisons that you said you're going to do. It's just a different type of setup, right? You wouldn't be able to get away with saying, well, there's actually nothing going on here, never mind. They don't like that if they've given you a bunch of money. So, so that is a little heads up, right? So that's what's going on in example 8.8 is the overall test was not significant, but they still go ahead and do the comparisons because that's how it was planned. All right. Any questions before we get on to 8.4? I'll just check here. Oops. Okay. Okay. Yeah, it's still so laggy. I don't know. It must be the time of day or something.
Yeah.
I don't know. Yeah. Manuel, did you question it? Just, yeah, it is laggy. My screen or Okay. All right. So, any questions though about 8.3 before we start 8.4? Okay. Let's see, I'll start a new, maybe. So 8.4 is on non-parametric statistics. Non-parametric statistics. Did you guys do it when I say non-parametric statistics? Does that ring a bell from 30 or maybe some other course that you guys have taken? No. So anyway, non-parametric statistical method. We've assumed that we pulled from a normalization. So that's one of the conditions that we have been checking, right? And so non-parametric methods are when the data are not required to follow a particular distribution. So the data are not required to follow a particular distribution. Such as a normal distribution, right? We've assumed that we've got this normal distribution, and so that's part of the assumptions that we check. And so there are some non-parametric statistics that we can run. We are just going to use software to do them, right? So this whole chapter is just about introducing different things that you could do, right? So it's not really about applying them necessarily, it's more about knowing about them. So what we've got is we'll first talk about a two-sample non-parametric procedure, and there are others, but this I would say is the most common one. And then we'll extend it to multiple samples, right? So basically going from a two-sample t-test to an Anova is what we're doing, but in non-parametric situations. So a two-sample non-parametric procedures. Two-sample non-parametric procedures. Or I'll just say procedure. The Wilcoxon Mann-Whitney test So what happened was, I think Wilcoxon was working on a method, and then Mann and Whitney were working together on another method. They basically landed at the same idea, so we just use them as a combined method. But the Wilcoxon Mann-Whitney test procedure is used to make inferences for two medians, right? So we've been testing means so far, but if we don't have a normal distribution, we know that we should use the median as our center, right? And so the Wilcoxon Mann-Whitney test procedure is used to make inferences for two medians, right? So medians are the best measure of center for non-normal data, right? And this is going way back to kind of the beginning of Stat 230. So medians are the best measure of center for non-normal data because they are robust. They are robust to outliers, right? And so these non-parametric tests, right, or these non-parametric procedures usually rely on the medians because they're more robust to outliers. So just for notation, we're going to use theta. So we will use theta subscript I to denote the population median of group I. To denote the population median for group I. So that I'll put a little theta I to denote the population median. Our conditions, and the conditions are actually going to be the same regardless of if we're comparing. So here, right, we're just talking about two samples, right? When we extend this, oh, it's lagging again. So here we're talking about two samples. Even when we extend this to multiple samples, the conditions are going to be the same. So that's nice. So the conditions, and I'll just put here, will be the same for multiple samples. Right, this is for two samples, but it's going to be the same for multiple samples. The error terms must have these properties. Must have a median of 0. Must have median 0. Follow a continuous, but not necessarily a normal distribution. So they must follow a continuous, but not necessarily a normal distribution. It doesn't even need to be symmetric. Doesn't even need to be symmetric, which is pretty cool. Right, so we don't even rely on symmetry if we're doing non-parametric methods. So, but the error terms, the last thing is that they must be independent. So of course, our observations still have to be independent, essentially centered on 0, right? They must have a median of 0, and they have to come from a continuous distribution. The requirements on that continuous distribution are way more relaxed, right? They don't have to be symmetric even, and so they don't have to be normal. And so the Wilcoxon Mann-Whitney test, Wilcoxon-Mann-Whitney test has a null hypothesis that theta 1 equals theta 2, right? medians are equal. And of course, the alternative hypothesis is that they're not equal to each other. Theta 1 does not equal theta 2. So what we've got here is in this Wilcoxon Mann-Whitney test, right? You might even see WMW. That's just the Wilcoxon Mann-Whitney test. You've got group 1 and group 2. Remember, this is just for 2 samples, and then later we'll do the extension to multiple samples, but it'll have the same layout, right? And so what's interesting about when we're analyzing the medians, right? So these thetas are medians. When we're analyzing the medians, we're usually doing these tests based on ranks. And so here, non-parametric tests are usually based on ranks. So what this is going to look like, right, is you take your 2 groups, or later your multiple groups, and then you sort those and then combine them. So I'll put in brackets, combine them. Then you're going to sort all these from smallest to largest. Sort from smallest to largest. And from that, you can rank them. Or rank the observations, I should say. Rank the observations. From here, if H naught is true, which says that theta 1 is equal to theta 2, right? The medians of these 2 groups are the same. Then the largest overall observation, right, from your rankings, right, then the largest observation should be equally likely to come from group 1 as it is from group 2, right? So it shouldn't matter which one is which, right? And so if H naught is true, then the largest overall observation is equally likely to have come from either group. Likewise, for the second largest observation, and so on and so forth. Likewise, for the second largest observation, etc. But if you've got your data sorted and ranked and you're finding that all of your highest ranking values are from group 1 and all of your lower ranking values, even if there's a little bit of overlap in the center, if you've got your lower ranking values coming from group 2, well, that's an indication that the medians are not going to be equal, right? And so what we do is we do calculate the average rank, right? And so therefore, the average rank of the data from the first group should be roughly equal to the average rank of the data from the second group. So we are dealing with averages, and how we compare those averages, it wasn't actually clear, and I don't really remember actually, because I don't really use non-parametric tests myself. But I'm assuming we use just a t-test for comparing averages. But we're not going to do any of these, so it doesn't matter. So the average rank of data that came from the first group should equal, oops, should equal the average rank of the data from the second group. The data from the second group. One thing to keep in mind is that if you have a tie in the ranks, and it's a tie between two groups, then you would have to make sure that your p-value is adjusted for that. And so here, if there is a tie in the ranks, between two groups, right? Or in general, right? I'll put the between two groups in brackets, just because, just as well in general. So if there's a tie, we need to be able to deal with that. So if there's a tie in the ranks, especially if it's between two groups, we should use adjusted p-values, which is just something that you would just tell R to do, and it should even use it as a default, but I'm not 100% sure. So if there's a tie in the ranks, we should use adjusted p-values, which, oops, p-values, which we just specify in R. Textbook actually uses output more from Minitab than from R. It looks like the Minitab output is quite a bit more detailed, whereas the R output just gives you the overall test statistic and the p-value, which is all we need. But the Minitab output seems to be more, I don't know, detailed. But we'll just use R, it's fine, we will survive. Okay, so the Wilcoxon Mann-Whitney test is for comparing two samples. So that would be the t-test equivalent, right? The two sample t-test. If we're comparing, so to compare more than two samples, we use the non-parametric Anova, parametric Anova, which is actually called the Kruskal-Wallis test. Kruskal-Wallis test. Okay. The Kruskal-Wallis test, oops, I should capitalize that. Kruskal-Wallis test has the same conditions, as the Wilcoxon Mann-Whitney Mann-Whitney test. So the error terms, just to recap, the error terms must have a median of 0, follow a continuous distribution, and must be independent. One thing to keep in mind is that even though they just have to follow a continuous distribution, right? So we're not putting any conditions on the shape of that distribution. One thing to keep in mind is that the different distributions, should have similar shape. Oh, it's not keeping up at all. The different distributions should have similar shape and only differ in their medians. The thing is, that's not an explicit condition. We can be a little bit lenient on that even. But it is something that you would check for, right? If you're doing one of these tests, is you don't want to be comparing medians from differently shaped groups, right? So you want to have roughly the same shape. So the Kruskal-Wallis test has a null hypothesis very similar to the Wilcoxon Mann-Whitney test, where you're just testing if, theta I, theta 1 is equal to theta 2 is equal to theta 3 is equal to all the way up to theta I. If you have I different groups, and then the alternative hypothesis, HA, is that at least 2 theta i's are different. So at least 2 theta i's are different from each other, or are different. Okay. We don't need to talk about the calculations. So all calculations would be done in R, or all calculations are done using software. It's basically, it lands you at an approximation using a chi-squared, and so it has the observed minus expected in some ways, so for the ranks. But like I said, all calculations are done using software, and so we really don't need to talk about what those calculations are. They're beyond the scope of this course. We do not need to worry about it. So, I'll put in bracket there. Calculation details are not needed. Not something that we need to concern ourselves with. It's more a matter of, if I ask you, okay, you want to compare the medians of these four groups, what tests would you use? You would use a Kruskal-Wallis test. And what's your hypothesis? It would be that theta 1 equals theta 2 equals theta 3 equals theta 4. What are the conditions? Well, the conditions are that the error terms must have a median of 0, must follow a continuous distribution, and with similar shapes for each of the groups, and the error terms must be independent. Right, so that's kind of more along the lines of what I expect you to take from this chapter, or this section, I should say. Any questions about that before we do 8.5 real quick here? I'll just check questions over here, but I think under control. So let's do 8.5 then. 8.5 is about randomization F tests. So the F test that we've been using, it assumes a probability distribution, right? So it assumes that we can follow an F distribution, and so we have to check all these conditions, right? And so the F test we have used so far, well, and also in regression, but that was an Anova, right? So the test we've used so far assumes a probability model. What's kind of womp about section 8.5 is that we're actually I'm gonna show you another way that we could find p-values for an F test without using a probability model, right? But the results are usually the same, so I'm not sure why. It's just to expose you to another way that we could do it, right? And so if you use probability methods to assign the treatments, right? And so if you're using some sort of random assignment of the treatments, so if you use probability methods to assign treatments, you automatically get a built-in probability model to use for inference. So you automatically get a built-in model, or built-in probability model, I should say. Built-in probability model to use for inference. Okay. Which means that the errors don't have to be normal. Errors don't have to be normal, which is one of the things that we have been checking, right? The independence here is going to be automatic because we've randomly assigned treatments. We have looked at method, like where we use probability methods to assign, just randomly assign treatments. The independence is automatic because they're randomly assigned, so we can assume independence, and the size of variation doesn't matter. The size of the variation doesn't matter anymore, because what we'll find is that, or we won't find, but what you would find is that even if you did transformation to try to deal with different variances, you would end up at the same results. So here, what we're saying is that the model depends only on whether treatments were randomly assigned. On whether treatments were randomly assigned. So basically, got a question here. If we're using non-parametric tests, range would be a good measure to identify the spread. That's true, yeah. But we don't actually, we can still look at the spread the same way that we have been using, just using side-by-side box plots or dot plots. So we don't actually need to rely on the range, but that is true, right? The median and the range go together. So, so that is true, but we don't need to rely on that. In fact, it doesn't even matter. The size of the variation doesn't matter. So we are assuming though that that as long as the treatments were randomly assigned, there are no conditions that we need to check. So there are no conditions to check if the treatments were randomly assigned. So here, what we're going to talk about just briefly is a randomization F test for one-way Anova. Randomization F test for one-way Anova. So what we're going to do, and we didn't get through the randomization section for regression, but we can do the same thing for things like the correlation is one that we do a randomization test for. And basically what we do is we generate a bunch of F's. So what we do is step one, calculate the observed, so calculate the observed F of your data. Right, so this is the one, this is what we'll call the F observed. Okay. Wait for it to catch up here. Then what we do, so this is the observed F. Then what we do is we randomly assign each of our observations to different groups. Right? So step two is to find the randomization distribution. Find the randomization distribution. Oh. So what you're going to do is you're going to re-randomize the data. using a computer, of course. And then, so you're going to re-randomize the data. So reassign all your observations to different groups randomly. And then you're going to compute and record the F statistic. The F statistic, which we'll call F rand. And that's a randomized F. So that's one time. Then you're going to re-randomize the data again, and you're going to repeat a large number of times. Repeat this a large number of times. Right. Usually about 10,000 should be enough. Yeah. Technically, kind of a side note here is you could re-randomize for all possible combinations, right? And so here, what I'll say is we use 10,000 randomizations, but in theory, we could consider all possible assignments, right? We could consider all possible assignments of all our observations to all the different groups. And so in theory, we could consider, all possible assignments, of n response values to groups of sizes n1, n2, n3. Oops, sorry, my hand really hurts here. N2, N3, all the way up to N1, or Ni, sorry, by calculating capital N factorial over N1 factorial times N2 factorial times Ni factorial. That's going to be a huge number, right? Even if you consider something small like 20 response values, right? 20 factorial is going to be, what is 20 factorial? 20 factorial is 20 times 19 times 18 times 17 times 16. I'm not finding my factorial button on here, and I'm not sure it would even be able to do it. But that's okay. Oh, here, second factorial. Hmm. 20 factorial. It's not doing it. Oh well. But what we've decided, right? But 10,000 is large enough, right? So we don't consider every single combination. We could, and this is how we would do it. But what we've decided is that 10,000, that should be sufficient. Okay. Then the last step that we do is, so now we've got this distribution of all these randomized Fs. If the observed F value that we found from our data, right, if there's nothing going on in our data, then this observed F should fall somewhere in the middle of this randomized F distribution. And so here, step three says that the proportion of F rand values that are greater than or equal to the observed F observed, is the estimate of the p-value. Is the estimate of the p-value. One thing, right, is that this p-value and the p-value that we've been seeing are often very similar, right? And so this isn't something that you need to do. It's just another way of doing it, right? And so here, one thing to note is that this p-value will often be similar to the p-value we get in our initial Anova where we find F observed, right? And so it's just another way that we could do it. If we don't get a p-value there, then this is one way that we could do it. Right? So a little bit weird, but like I said, chapter 8 is just introducing little things that you could do, and often, you know, we don't need them, but it's just good to know. All right, that's all I've got for today. I know I went over time, but do we have any questions? Okay, nice. Any questions? So we don't need to use the lab time today. I mean, you can use it, but there's nothing to work on. So if there are no questions, then that's all I've got for today.
Thank you.
All right, awesome, thank you. Cool. Then I will not see you, but thank you. You'll hear from me on Wednesday then. Awesome. Thanks, guys. See you later.